Good afternoon and welcome back to CENG 3325 Structural Analysis. This is going to be part 2 of lecture 29 in the video series, and here we are going to be looking at approximating vertical loads in building frames. So in part 1 we looked at approximating or approximate methods for truss analysis and also why you would use approximate methods. And we're going to do the same thing except now applied to frames and vertical loads in building frames. And then part 3, we'll look at horizontal loads in building frames. So approximate method, let's consider approximate methods for vertical loads in building frames. Vertical loads in frames. So just like in the case of trusses, we're going to have two different cases. All of these cases are going to be two different things. Or are going to be different, classified differently than our previous case, although it still is going to depend really on relative stiffness. So case 1 will be if you have, let's say you have very stiff columns relative to beams. And our second case will be if you have very stiff beams relative to columns. So if you have great big columns and very light beams, we'll be looking at case 1. And if you have great big beams and relatively light columns, we'll be looking at case 2. So let's look at each of these. And first of all, let's consider the problem here. Why would we need to do this? Well, the problem here is consider something like a fixed frame. Consider something like a fixed frame. If you have a frame, and let's say this is fixed, like this here, well, this frame is going to be very statically indeterminate. We can look at the equations we saw previously in the semester to determine the exact degree of indeterminacy and all that, but this is obviously going to be statically indeterminate. So what I would really like to be able to do, though, is maybe make some approximate method, and maybe I can apply some sort of approximate method to figure out, okay, how is this going to behave approximately, or how can is there some assumption that I can make that will make this into a statically determinate system? So if you look at your normal frame, if you look at a frame with fixed connections, how does this actually behave? If you look at a system with fixed beams and fixed columns, or a beam fixed to columns, when this deforms, well, if you have equal behavior, if you have, for example, if you have very stiff beams, or if you have beams and columns of equal stiffness, well, depending on the relative stiffness of this, you're going to get some, when you apply a uniform load on this, towards the middle you are going to get some kind of positive bending. Towards the middle you're going to get positive bending. So we tend to get positive bending toward the middle and negative bending toward the outside. So you get inflection points somewhere in the middle. Because in order for this beam to curve down here and still remain horizontal at the ends, it has to go through a shape kind of like this. And the only way for that to happen is to have regions of positive bending and negative bending. And crucially, if you think through the derivative relationships of shear and moment, the inflection points will be points of zero moment. Will be points of zero moment. And we can consider these as pins. And we can approximate points of zero moment as pins. Points of zero moment as pin connections. So both cases 1 and 2, well, both of these will have some point where we'll just assume that there is a pin connection in our beam, And in turn, or the only difference between them will be what distance we assume that those are out from the edge. Okay, so let's consider this. Again, essentially we're going to, again, let me move on here and say that due to the nature of fixed-fixed connections, or due to the nature of fixed-fixed beams, we will have regions, we'll have a region of positive bending in the middle, assuming your loads are downward, of course. Assuming your overall thing is under a downward loading, downward W, we will typically have a middle region of positive moment and outer regions of negative moment. And the distance between the distance of this transition of these transition points, or the location of these transition points, depends on relative column beam stiffness. On column beam stiffness, relative stiffness. On column beam relative stiffness. All right. Excuse me. So let's consider this on column beam relative stiffness. So let us consider this for a moment. And again, as I mentioned, those points where we'll assume we have zero moment can approximate points of zero moment as pins. Of zero moment as pins or moment releases. Okay, so let us go through each case. Case 1, again, is going to be, as I previously mentioned, very stiff columns relative to beams. So the first one will be the stiff column case. Now, this is, again, about relative stiffness. So stiff columns, and when I say stiff, I'm talking about bending capacity. So if the M max, the bending capacity for the columns, is much greater than the M max for the beams, then you'll have the stiff column case. Then you'll have some sort of stiff column case. So let's look at this. So let's say we have a fixed beam, and how can I approximate this for the fixed column case, or the stiff columns case? So we have a beam here with a fixed connection, fixed in either end from the strong columns. And then there will be a distributed load across the top of it. Excuse me, I'm a bit under the weather. So we have a distributed load W across the top of this. Now, as this is statically indeterminate. However, what we are going to do is we are going to approximate this with or what we can do with this is we can approximate this with the following pin system. So on the left and right ends, we're still going to have, excuse me, we are still going to have a pin, or a fixed piece, but in the middle, we are going to have pins. So we can think of it a couple different ways. I can think of it with pins like this, and like this. Or another way I can think of this with line diagrams would be if I had something like this, a pin, and a cantilever beam. So basically cantilever, pin, middle section, pin, and then the cantilever. And the locations of these, the real critical difference is between the two cases is going to be the ratios here. So if this entire thing is length L, this distance on either side is going to be 0.2 L. 0.2 L, and this would be 0.6 L and 0.2 L. So in other words, what we are assuming is the curvature ends up going something like this. We're assuming the beam would be in positive curvature here, and then negative curvature up to about there, and negative curvature up to about there, negative moment. And so again, this will be the region where we have positive bending and then we have negative bending, and the inflection points where we switch and the points where we have zero moment will be 0.2 L from the left hand and the right hand sides. And again, this is for cases where you have very stiff columns or where the bending capacity of the columns is much, much greater than the bending capacity of the beams. And of course, now we don't get rid of the W on either of these sections. We do have the same W all throughout. It's just that we have we can put some releases in here, and this makes the, when you run through the structural analysis, this does make this a lot simpler. Then if you have a case of very stiff beams relative to columns, so here, case 2, very stiff beams relative to columns, we're going to do something similar but slightly different. And again, by relatively stiff, what I mean is the M max, the max moment capacity for the beams, is much, much greater than the max bending moment capacity for the columns. And in this case, we're going to set up something very similar, but we're just going to put different ratios for the L's. So essentially, we're going to assume that the point of zero moment is 0.1 L rather than 0.2 L. So here, let's see. Or actually, sorry about that. That's not quite right. If we have very stiff beams relative to columns, we would basically have pure fixed beams. Or sorry, pure pinned connections. So in the case of very stiff beams, a beam would normally tend to rotate at the ends if you support it, but what's ultimately going to constrain that rotation is the stiffness of the columns on either side. So if you have two columns here, and you apply load to this thing's going to want to bend, and what's going to prevent that bending is the columns bending capacity. And so if the columns have very, very, very extremely little bending capacity, then you can basically treat this as a pin connection, at which point you would just draw this like this. You would just have a pin connection. Well, you'd have a pin connection on your beam without having the column be interrupted. So basically this would, well, I guess you could put a pin in the frame as well. So you'd end up having something like this. Pin connections on your frame here. Like this. Or you might also approximate this with, again, with the pins being over the entire L. Or I would probably be a little more comfortable saying that the columns themselves will be able to transfer stiffness between each other. But if the beam wants to bend, they're going to bend. They're going to bend along with it. So essentially the columns, the beam is free to bend, but the columns will bend along with it, but the columns will be able to pass bending load along themselves. So I don't know if I'm really comfortable putting the pins exactly there. Maybe another way you could think about it is, I could almost think of this as a case where we do have the fixed and the pin like this, but it's so close to the edge, it's basically 0. Like where maybe I could call that like, oh, I don't know, something like, maybe that's like 0.001L or something like that, and that's 0.001L. So a case where it's basically a pin, but still the column is able to transfer moment up and down its own height. So if you know you have extremely stiff columns or extremely stiff beams, you can use this assumption. Extremely stiff columns or extremely stiff beams, you can use this assumption. However, in reality, we tend not to use either one, even when doing approximate methods. And the reason for that is that, think about this, it is rare that you have either extremely stiff beams or extremely stiff columns in building frames. That you have one extreme or the other. Things tend to be matched up, especially if you have fixed connections rather than pin connections on your beam to column connections. You tend to size things of similar stiffness. Columns and beams tend to be of similar stiffness, especially if you're relying on your columns to carry moment. And beams really tend to be of similar stiffness. They do tend to be of similar stiffness, so we really can't use either condition. Even for approximate methods, neither is ideal. What we can do though, or I really cannot use either scenario or condition or case, maybe the best way of saying that, even for approximate methods in most cases. But what we can do is average them. So, if beams and columns are of similar stiffness, then a reasonable approximation is to say, hey, if M max of the beam is approximately equal to M max of the column, why don't we just average the response or the behavior? Maybe we can say the behavior is approximately 1/2 or the average of the stiff beam and stiff column case. The stiff beam case and the stiff column case. And the stiff column case. So what if we just average these together? And how would we average these together? Well, I basically assumed 0L for the distance to the inflection point here, and I assumed 0.2L for the distance to the inflection point there. So why not just assume 0.1L? So I could assume this. And this is going to be our typical approximate method if we have a fixed frame and we don't know anything about the relative stiffness, or we just assume they have relatively similar stiffness. I will tend to assume 0.1L and 0.1L and 0.8L in the middle. 0.1L, 0.8L, and 0.1L. So what I can then do is, if I have a frame, again, unless I know something about the relative stiffness, I'm just going to go ahead and assume everything is 0.1, 0.8, and 0.1. And so if I have let's say I have a frame. Let's say I have a frame like this, even a 2-story frame or something like that, or even multi-story, with fixed supports all the way around. This would otherwise be quite intense to analyze, but if I can, and it is something I generally want to use a computer for, but I still need somewhere to begin. I need something to put into my computer program initially. So maybe I have loads like this, and like this. And let's say the dimensions on here are maybe, oh, I don't know, maybe 20 feet across for each bay. Let's say it's 20 feet across on each bay. Well, what I could do is I could then approximate it with the following system. I could approximate this frame and thus make it statically determinate by doing this. So the columns remain unaltered, they'll still have fixed connections down here. Maybe they're going to do this, and then they'll have a pin and a pin, a pin and a pin, and then the interior column fixed down here, cantilever and pin, cantilever and pin, midspan, midspan, pin, pin, cantilever, cantilever, and then the exterior beam, or exterior column. And we'd have the same W all the way across. That's not going to change. It's the same W if this is W and W. I might have the same W all the way across. And the same W here. Just depending what my initial loads were, they're not going to, just whatever my initial loads are, we're just going to put the same loads on this now, a little bit more complex, but much simpler to analyze and statically determinate structure. W and W. And the lengths here, since I said 0.1, well, 0.1 or 1/10 of 20 will be, let's just go ahead and draw this. Draw my dimension lines. Let's see, the total is 20, so 1/10 of that is 2 feet. That is 2 feet. That would be 16 feet. That would be 2 feet. That would be 16 feet, and that would be 2 feet. And that is an approximate way I can then turn this otherwise statically indeterminate frame into something that I can analyze with relative simplicity and relative ease. And again, using that, I could then, doing this, I could get my initial member sizes, at which point I would then want to typically do a more exact method, more exact analysis using something like the force method, virtual work, or using a computer analysis program. All right, but that'll do it. That'll do it for part 2 here. I will later record a part 3, but this will just show you an approximate method for handling or for breaking down fixed structural frames into something that is statically determinate and reasonably accurate, or at least accurate enough for simple hand calculations or for initial sizing of members. All right, that'll do it for now. Thank you all for watching. Let me know if you have any questions, and as always, thank you.